Chapter 2, the physical layer, computer networks. Communication satellites. Now, communication means sending, receiving of information, data. Satellite is that instrument, that object in the celestial sky and behaving as if it is like moon, following all the laws. So how it started? In 1950s and early 1960s, there were people who actually at that time there were metallized weather balloons already there. So people tried to use this metallized weather balloon in order to communicate. That is, they wanted to set up a communication system by bouncing signals of these metallized weather balloons. This was a very good try and inventive thought. But unfortunately, the received signals were so weak that the communication cannot be set up. The communication system cannot be set up because the received signal was very weak. Now you see here moon. Now comes the US Navy. US Navy built an operational system, a proper operational communication system between ships in the water and the shore, that is the land. So they built an operational system for ship-to-shore communication by bouncing of the signal from where? From the moon, the natural satellite. So what is the difference between an artificial satellite and a real satellite? The difference is the artificial satellite means the satellite which we will send and it will behave like moon. That is, it will set up and it will go round and round Earth following all the, as I say, the laws, gravitational law and etc. So the artificial satellite, they can amplify the signals before sending back because moon doesn't know what we are sending. So it will just strike, the signal will strike, it will bounce off and whatever you will get, you will get. That is, the signal will be bounced off from these actual satellites like moon. But as I am suggesting, the artificial satellite, because we are making it, so we can make the provision that the signals which are being sent back, because uplink is sending from ground to satellite, downlink is from satellite to the ground station. Okay, so we can put some digital signal processing and amplification so that what we get is usable. So communication satellite, you can imagine this as a very big microwave repeater, not on the ground, but in the sky. So you know that we have been using the microwave links and we put 50 kilometers repeater in order to enhance the signal strength. And the same thing is happening in the sky. So you can imagine communication satellite as a big microwave repeater in the sky. In this satellites, there are certain transponders. For example, some spectrum is being given to you as a satellite manufacturer or user. Now the transponder, each transponder will listen to some portion of the spectrum. Today we have around 40 transponder in the present satellites, maybe more than that. So the main idea is to amplify the incoming signal, that is when the uplink, that is from ground station to the satellite, the signal goes, it is being amplified, the energy is reboosted and then it is rebroadcasted. Please remember, satellite is broadcasting. So it is rebroadcasting it at some another frequency to avoid interference with incoming signal. Why I am saying that the frequency is different? Because the incoming signal is at certain frequency, the the downlink has to be in another frequency. Otherwise, there will be some interference. Okay. Now, this is the picture of a ground station doing uplink and downlink. And the mode of operation is known as a bent pipe. What all I explained you, this is called the bent pipe. Now, what you can do here is, what people have done is, the digital signal processing or digital processing can be added here, because this can be added on board. Whatever data stream is coming or the signal is coming, so we may be able to manipulate, clean, change or make it better for the downlink in the overall band. This can be done. So there are various ways, because in digital signal processing we have various Fourier transforms, we have the image cleaning, data amplification, morphing, whatnot. So all these digital processing can be done on board so that you get a proper on the ground. Or this digital information, this can also be received and this can be rebroadcasted by the satellite. Now, when you are regenerating the signal, it will improve the performance, because in bent pipe, whatever is being sent is being received, though there is some amplification. But regenerating the signals using the digital signal processing, it is better than the bent pipe, as satellites does not amplify noise in the upward signal, because noise will always there. If you send something to any sender or receiver, then you will have noise. You cannot get rid of that. Cleaning the noise and then amplifying will give you a clean data and the signal. So the downward beams can be broad and it can cover a substantial fraction of the Earth's surface. What does it mean? See, this is a satellite. Now, or you can imagine that you are standing there. How much you can view? The field of view will be higher as the altitude increases from the surface of ground. So you can also have the very narrow kind of you can say footprint covering an area only hundreds of kilometers. So this depends on how the manufacturer have made it, satellites. In communication satellite or all the satellites, the Kepler law, as I said, they are applicable. First Kepler law is the orbits are ellipse, because it's all gravitation happening, and the orbits will follow a egg-shaped structure, not a circular. So orbits will remain as ellipse. This is the first Kepler law. Elliptical, it will be elliptical. The second Kepler law is equal areas in equal time. For example, in the same time, two areas are covered or two lengths are covered. If you join this center and join this center, this area, shaded area, will remain equal. That is the Kepler second law. And the third is the time period is directly proportional to the radius. What power? Power to the 3 by 2. That is, let me just make it like this. T square is a cube. That is, let us write a as the radius. So T square is directly proportional to r cube. Now let us multiply both sides by 1 by 2. What do you get? The time period is directly proportional to the 3 by 2 power of radius, that is r to the power 1.5. So the orbital period of satellite varies as the radius of orbit to the power 3 by 2. These are Kepler law. So the Kepler law is applicable to every satellite because it is following the rules and law, because it is in the sky. You have established it in the sky. So higher the satellite, longer will be the period, and this is quite common sense, and this is very logical also. If the Earth is there, and what is the period? That is when it is rotating, or you can say completing the whole circle or ellipse. That time, the low orbit satellite, that will pass out fairly quickly. Why? Because it is at a smaller distance. It is called the lower, or you can say LEO orbit. The Jio orbit is quite far, 36,000 kilometers. A Geo, 24 hours it takes to make a complete time period for orbit. At the same time, the Earth also revolves around its axis. That is, the geostationary will remain as it is. So many of them are needed to provide this low. I'm talking about LEO. LEO, we need more of them because we want the continuous coverage, and there has to be some ground antennas that must track them. So geostationary is like you are standing and you are viewing a large area. The low Earth satellite, they are viewing a lesser area. For that, you need more of them. Let me give you numbers now. This is 36,000 to remember, but to be precise, it is 35,786. So 35,800 here, but the exact number is 35,786. This is the period. The period is 24 hours. That is, in order to orbit, means complete its orbit, it will take 24 hours if it is at a distance of 36,000 km from the Earth's surface. Okay, that is called the geostationary satellite or geosynchronous satellite, because it is moving in at the same time, it is taking same time as the Earth is revolving around its axis. Now take the distance as 384,000. The period is what? 1 month. You know about moon. Moon does that. So as the distance increases, the orbital period also increases. At 384,000, it will be 1 month as the moon is doing, because moon is also a satellite. Though it is not an artificial satellite, it does like that. Now, one important factor here to understand is the Van Allen belts, because satellite period is one of the consideration. There is one more consideration or another issue is the presence of these Van Allen belts. What are these Van Allen belts? How do you know that this moon is revolving around Earth? Because of the magnetic field. Okay. Now Earth has magnetism, so there are layers of highly charged particles which are trapped by the Earth magnetic field, and these fields are nothing but the Van Allen belts. These are called as Van Allen belts. Let me just show you the places, because these Van Allen belts, if you are sending the satellite or trying to establish, it will be destroyed in particles. So these factors, we only have 3 regions in which the satellites can be placed safely: LEO, MEO and GEO. Okay. Now the people will ask, what about these places? Why are we are not putting in between? The answer is Van Allen belts, because here the satellite will be destroyed in pieces, in particles. So let me show you here. The red and the yellow part, this is the Van Allen belt. This is the inner belt, around 1,000 to 800 miles, 8,000 miles, and you cannot have satellite here. So it can be between Earth and the first belt, or it can be between the first belt and second belt. The second belt, outer belt, which is 12,000 to 25,000 miles. You cannot have any satellite here. So in between Earth and the first inner belt, or between the first inner belt and the second inner belt, and after the second inner belt, these are the only 3 possibilities. So which is near to the Earth is LEO. Between the first inner belt and the second inner belt, this is the MEO. GPS satellites are here. And finally outer, that is the outer, those satellites which are outer of the outer belt, which are placed here, are called the geosynchronous or geostationary satellites, GEO. This is called the Jio Orbit. Okay. So this Van Allen belt is a criteria. You cannot have satellites here. Geostationary satellites, geosynchronous satellite. We are discussing geostationary satellite, but before that, you need to understand geosynchronous also. Geostationary is that those satellites which are at 36,000 km and they are orbiting in the equatorial plane of the Earth. That satellite which you established at 36,000 km, and a person will always see that satellite because it will seem to be stationary, because Earth will go around its axis, complete its 1 day in 24 hours, complete a revolution, and this is rotation. And the satellite will also take the same time at 36,000 kilometers. So that is the stationary. Geosynchronous, you can say it has some angle from the equatorial plane. It is not at the equatorial plane. There will be an angle of inclination. So this is more polar. This is more inclined polar because the geostationary will not cover the polar areas. If you want to cover the polar areas, this geostationary has to be geosynchronous. So this question is asked normally, what is geostationary, what is geosynchronous? Let us come back to geostationary satellite. Now here is Arthur C. Clarke. In 1945, he is not a scientist, he is not any, a NASA person. Now you have to salute this guy. Why? Because he was just a writer. He was a science fiction writer. Arthur C. Clarke. What he did, and why I am praising him, because in his books, in his fiction stories, he calculated in the science fiction that a satellite at an altitude of 35,800 kilometers in a circular equatorial orbit would remain or would appear to remain motionless in the sky. Did I just tell you? I told you because we have science, the technology has advanced. But in 1945, Mr. Clarke has already written as a fiction that at this particular distance, he gave the exact number also. At this distance, there will be satellite and this will remain motionless in the sky because the time Earth takes to complete its one rotation, the satellite will also take the same time to complete its orbit. So he completely described the communication system that use this. He said that will be manned geostationary satellite. He wrote about the orbits, he wrote about the solar panels, he wrote about the radio frequencies, even the launch procedures. And he was just a writer. He was not a scientist. He was not from some space research organization. Unfortunately, what he said was that there will be walls, at that time. So he said it will be impractical. The satellites won't be able to work. It is impractical. So he gave all the idea, all the science, all the theories, all the numbers. And because he was writing, he said it will not be possible because at that time the transistors were not there. But after him, the invention of transistor, they changed everything. Because his idea was how to give the power, how to keep rotating, how to keep all those the technology and machinery working. So the invention of transistor changed everything. And now you have to remember 10 July 1962, this was the day in aviation that changed history. And this is not about changing the history of aviation. This was the first artificial communication satellite called Telstar, and this was launched in July 1962, 10th July 1962. These high-flying satellites at 36,000 kilometers seem to be stationary are called Geo or Geostationary Earth Orbit Satellites. Okay? So we'll call them as Geo, G-E-O, Geo. So I'll give you an example. Because it is an equatorial plane, so assume it to be 360 degree where the geostationary satellites can be placed. Because this is a very precise orbit. So it is technologically unwise to have this geospace much closer than 2 degree in the 360 degree equatorial plane because there will be interference. We need to have at least 2 degree of difference. So with the spacing of 2 degree, what will happen? Only 180 satellites, 180 geostationary satellite can be placed. But there are people, China also wants to do it there, Japan also wants to do it, even India. So in order to prevent the chaos in the sky, the orbit slot allocation was done or is done by ITU. ITU is International Telecommunication Union. So they said, okay, we will tell you what the allocation we can do for you. So modern satellites, if you see, they are very large, huge, weighing over 5,000 kg. 5,000 kg. They have solar panels, so they are consuming several kilowatts of electric power which are produced by the onboard solar panels. But because they are in the sky, they are not in that much control of the ground station. Sometimes there will be effect of solar, lunar and planetary gravity. Because if you leave your kid outside to the hostel, it may happen that he may just lose his way. So same thing, the effect of the solar, lunar and the planetary gravity, it moved them, these satellites, from their assigned orbit slots, which has been already assigned by the agencies. And orientation can also be drifted. So this is an effect which has to be countered. And this is countered by the onboard rocket motors. There are onboard rocket motors that will always make arrangements so that the satellite can be on its course, on its slot orientation. So this fine-tuning activity is called as station keeping. This is called as station keeping. And what happens after the life is done? In around 10 years, when the fuel for motor it will exhaust, the satellite will behave like, independent. So the satellite will drift, it will tumble. So the ground connection has to be turned off. So it needs to be turned off after certain years. So what will happen to the satellite? Will it be a space waste? But it will not be, because what happens here is this happens, it will die down, it will burn off. Okay, so eventually the orbit decays and the satellite re-enters into the atmosphere and it will eventually burn up like what you see in this picture. Okay, you have seen the meteors when they come, most of the meteors, 99% of the meteors, they just burn up, same way. Along with these orbit slots which we discussed at length, frequency is also an issue. Whenever we're dealing with any satellite, the frequency, because the downlink transmission, it will interfere with the existing microwave users. There is already microwave terrestrial links which are being established by various countries, various agencies. Now the downlink transmission, if they are having the same frequency, they are going to interfere with the existing microwave users. Okay, for that an agency has to come. So ITU has allocated certain frequency bands to the satellite users also. That these are the frequency you can use, because it should not be interfering with the microwave users. So how it started? The earlier time when it started, the C band was the first to be made available for the commercial satellite traffic, when actually satellite traffic were commercialized. So C band was the first. C band, the downlink was 4 GHz and the uplink is 6 GHz. Please remember, the downlink is always lesser than the uplink. Now you have to give me an answer for that. Why? So uplink is from ground station to satellite, what you said, and the downlink is what you get from satellite to the ground station. These are the signals I am talking about. So two frequency ranges, lower one for the downlink traffic and upper one for the uplink traffic. After that, the L and S bands were added in the year 2000. So this L and S band, then came the KU. U is Ku band. U is for K underband. And it is not that much congested as of now, and because it has higher frequency. L and S band were having 1.5 GHz, 1.6 GHz. S was 1.9 and 2.2 GHz downlink uplink. And when it comes to KU, it's 11 GHz downlink, 14 GHz uplink. So this is, as I'm saying, that it is not that much congested, because the frequency, as you see, it is higher. The bandwidth is also around 500 MHz. Satellites can be placed as close as 1 degree and transmission speeds up to 500 Mbps. The problem here in Ku band and Ka band is rain. Even in the lower part of atmosphere, stratosphere, etc., or troposphere, etc., we have water, or the humidification is there. So the water absorbs these short microwaves. Then the Ka band, K above band, for commercial satellite traffic, the problem is everything is good, but the equipments are quite expensive. Rain is affecting Ku band and Ka band both, but the equipment costs are also there. In Ka, it's quite expensive because the downlink is 20 gigahertz and the uplink is 30 gigahertz and the bandwidth is 3500 megahertz as given by the ITU. These are the ranges. So now coming to the transponder part of the satellites. Modern satellite, they will have 40 transponders and more, and every transponder, as I said, the spectrum will be there. So every transponder will listen at particular say a part of that spectrum, around 36 megahertz bandwidth for each transponder. And then this is the picture of the actual transponder, and each transponder beam is divided into time slots, so it will use the time division multiplexing. It will get the whole a particular time to send and receive. The first Geo satellite or Geo, it had a spatial beam. Spatial is the distance. Spatial beam that illuminated about 1/3 of the Earth's surface, around 42.2% to be precise. This is called a footprint. Let me just show you here. See, if you are, say, imagine yourself here. How much Earth you can see? It's your eye. Satellite is nothing but eye. You can have an analogy of the eye. So the field of view will be larger. In Leo, the lower one, the area will be lesser. So the footprint can be 1/3 of the Earth. Nowadays, each downward beam, this can be focused on a small geographical area. If you are from United States, why do you want to cover whole Earth? You will concentrate on United States. So multiple upward and downward transmission can take place simultaneously. So this small area or the field of view or the beam area, these are the spot beams. They are elliptically shaped like an egg, and they can be as small as few hundred kilometers in diameter. Now this picture you see here is of VSAT. VSAT. In geostationary satellite, you need to have a ground station, or the antenna has to be large. It has to be expensive. It has to be bulky. So, even order of maybe 2 or 3 playground. So then came the VSATs, low cost microstations. These are called very small aperture terminals. Now these VSAT VSATs, the antenna, parabola shaped antenna, the size was, there are tiny terminals. If you compare to the Geo antenna, that is geostationary Earth orbit antenna, 10 meters and above. These are tiny terminals. They have 1 meter and even smaller than that. So it is smaller, quite smaller than 1 meter. It can be handled quite easily, and they can put out power about 1 watt. So the power is also less. And uplink up to 1 Mbps and downlink also several megabits per second. So direct broadcast satellite television, they use this VSAT for a one-way transmission. So VSAT was also a revolution, because now we can use this to do certain various activity. The ground station, we call it as a hub. So you see here, I am showing you the VSAT. Let me show you here. We have the high gain antennas here. So this is a hub, VSAT. And how is the transmission taking place? This is a communication satellite. So from hub to satellite to the smaller VSATs, and from the VSAT to the satellite to the hub. So there has to be a hub, a big hub station. So here you have a hub station, a satellite, and you see even the internet and the file download all can be done using this very small aperture terminal, VSAT. This is how the technology has advanced. High gain antenna is needed to relay the traffic between the different VSATs. In this geostationary satellites, communication satellites, if you want to know the difference between the communication satellites in the terrestrial point-to-point links, because you see these are antennas and these are line of sight point-to-point links. So there are certain differences. There are advantages and disadvantages. Now, if you know the speed of light, it is 3 into 10 to the power. This is huge. 3 into 10 to the power 6 meter per second. Okay. 3 to 10 to the power 8. So that is 300,000 kilometer. Okay. This is not 3 into 10 to the power 6. It is 3 into 10 to the power 8. Now, even though the signal to and from satellite travel at the speed of this light, there is a long round trip. And this will introduce latency, that is a substantial delay for the geostationary satellite. So a typical round trip value will be 270 milliseconds. If you are using a VSAT system with a hub, it will be 540 milliseconds. The terrestrial microwave links, they have a propagation delay of 3 microsecond per kilometer. So the delay in the terrestrial microwave link will be 3 microsecond per kilometer. But if you talk about coaxial cable and the fiber optic links, what will be the delay? The delay will be 5 microsecond per kilometer. So you can see the difference. Micro is smaller, milli is higher. So the delay will be higher in geostationary satellite. Okay. Satellites, I'm talking about the security aspect now. So the satellites are inherently broadcast media. That is, it will send to everyone. Everyone can listen, everyone can understand, everyone can do whatever they want. So from the privacy point of view, the satellites, they are disaster because everybody can hear everything. It is broadcasting. So in order to keep the confidentiality, privacy point of view, encryption is essential. Encryption means, sending the data as if it is being changed. For example, if you want to send XY, you can send AB, and in the, retrieval, that is the decryption point, you can again change it to XY. So satellite costs of transmitting a message, it is not dependent on the distance traversed. It is same wherever you send. If you do a large beam, small beam, near, far, wherever you want to send. Satellite cost of transmitting any signal or message is independent of the distance traveled. Satellite, they also have excellent error rates. That is, the error rates are less and they can be deployed almost instantly. Most of the time, the government agency does that. Because if some disaster is there and the government has to respond or the military communication has to take place, the satellites are the best option. But there are disadvantages also. First of all, launching satellite is itself a very big task and it is costly also. We have Elon Musk, Jeff Bezos and Ambani's, they can do that now. But it is quite costly. And satellite bandwidth is gradually becoming used up. So from where the bandwidth will come? This is another problem. You cannot say disadvantage, but this is the thought, what you have to think as the upcoming technocrats. And there is a larger propagation delay or the latency in satellite communication than if you compare it with the terrestrial communication. So there are certain things you have to keep in your mind. This is your satellite based communication. This is your terrestrial wireless communication. So you have on the ground, you can have a point-to-point communication. In satellite, it is all about sending the data or signal to your satellite. It will amplify, do some digital signal processing and send it back through downlink to the ground station. So in satellite-based communication and terrestrial wireless communication, in the satellite-based communication, the area of coverage is higher. Because if you see a satellite, it can cover a larger area. Around 42.2% geo will cover. Geo satellites. So in terrestrial wireless communication, the area of coverage is not comparable with the satellite based. The satellite-based communication, this uses limited resources of spacecraft power and allocated bandwidth, because the ITU has provided the bandwidth and there is a limited power. But in terrestrial wireless communication, this uses unlimited resource in the Earth station and satellite. Okay. Now, the one more thing is, in the satellite, the time is invariant between the communicating satellites. What does it mean? In terrestrial wireless communication, there is no time variation between the two terrestrial wireless antennas. The precision in satellite is achieved accurately between the satellite communication. And when you talk about the terrestrial wireless communication, there is less precision between the terrestrial antenna. In the satellite, the quality of the transmission is extremely high because the satellite links are used in short-term basis. In terrestrial, the quality of transmission is low because the satellite links are used in long-term. In the satellite, very high bandwidths are available to the users, and in the terrestrial, bandwidths of data and the data rates are moderately available to the user as compared to the satellite-based communication. So, satellite, the delay time is higher. Terrestrial, it is less. Satellite broadcast to everyone. Microwave or the terrestrial link, they don't do it. Confidentiality is secure. MEO or medium Earth orbit satellites, this we are going to take in the next discussion. Till then, thank you so much. Take care of yourself.